Okay, now we're going to look at step 3 and 4, create a Bohr diagram and a Lewis dot structure. So the first thing we need to discuss is what valence electrons and valence shells are. So if we look at this example right here, each one of these circles, these rings, is a valence shell. Now, these are electrons, these dots are electrons that are drawn on the shells, and the ones in the outermost ring are called valence electrons. So how do we determine how many rings it has and how many electrons it has? So that is what we use our periodic table for. So if we look at our periods, every period is a ring. So all of the elements in this period have one ring, this period has 2 rings, this period has 3. We don't really go too much further than that. We might have one with 4, but for the most part, I think we do magnesium. For the most part, I would say 3 is the max that we do. So the tricky thing that you need to remember is that hydrogen is not the only element in its period. We got to go all the way across, and there's actually 2 elements in its period. So both hydrogen and helium have one valence shell. So how do we determine how many electrons are on that valence shell? It depends what number it is in its group or family. So hydrogen is the first element in its group or family, so it will have 1 electron on its one valence shell. Helium is the second and final element in its period, and group and family. So that means that it will have 1 valence shell because it's in the very first period, and it will have 2 electrons on that valence shell because it is the 2nd element in its group or family. Okay, it'll make a little bit more sense as we go. Again, this is a review from last year, so hopefully you guys already know a lot of this. So if we go to the next one, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, they all will have 2 valence shells. So they'll have the hydrogen and helium valence shell, which is full. So it'll have 2 on it. Then they will have a second valence shell, and depending on what number it is in its group or family, it will have that many electrons. So lithium would have 1 electron on its valence shell, its second valence shell, outermost one. Beryllium would have 2 on its outermost valence shell. Boron would have 3, carbon 4, 5, 6, 7, 8. And if you actually look, instead of counting, because sometimes counting gets old, you can look at these numbers with the A beside and it'll tell you what number it is in its group or family. So instead of counting all the way to 7 for fluorine, if I'm lazy, I can just look above it, see that's 7A and know that it has 7. Now you always have to remember to include the first valence shell with 2 electrons in it as well. So basically all we're doing is we're adding all of the electrons that it takes to get through the periodic table until our element. I gave you this little cheat as well. So if this energy level is the same as a shell, so if it's in the first energy level, it can have up to 2 electrons because there are 2 elements in that level. If it's in the second, it can have up to 8 because there are 1, 2, 3, 4, 5, 6, 7, 8 elements in that shell. Okay, so this is just kind of a cheat sheet. Instead of always having to count, you can just look at that. Again, we don't really in Science 10 look at these 4th, 5th, 6th, 7th. But I usually do explain that the only reason the 6th and 7th are 32 instead of 18, because again, we're counting all the way across our periodic table, is because the lanthanides and actinides actually go into these 2 squares, so you have to add those in. But again, that won't really matter unless you take a higher level chemistry class. So let's go through and do boron together. And again, that's in the example, so kind of got a cheat there, but that's okay. So we'll look at boron. Boron is in the second period, so it has 2 shells. They drew the shells for us, but later on, I guess it depends what we all do in this class since it's online, but normally I would have you draw your own shells. And I would also have you draw your symbol on the center, but it's okay if you skip that for right now. But normally we would draw that in the center. Some people like the nucleus drawn around it, so sometimes you'll see a circle around it. I'm not too picky about that. So we have our 2 valence shells. We have boron over here. Now we have to either count what number it is in its group or family, or look at the number above it. So if we want to count 1, 2, 3, or it says 3A right here. So we know that our first valence shell is full, and it can always have 2 in it when it's full. And boron has 3. Now for placement of the dots, it doesn't really matter. The only thing that is nice is if you kind of spread them out evenly, normally in quarters or halves or however, thirds in this case. Well, not really, I guess, but in quarters, I put 3 out of the 3 quarters. And then if you add more, then just double them up in pairs, because if you spread them out around the circle, like let's say you had 8 and you spread them all out, they're just harder to count. So if they're in couples, it's easier to just go 2, 4, 6, 8, or however many there are. So that is our Bohr diagram. Now, if you want, you could do your Lewis dot structure now, or you could do it later, but the Lewis dot structure, once you have the Bohr diagram done, is super easy. All we do is we just look at our outermost valence electrons. So we have 3, and we just add them on. So 1, 2, 3, and that's it. The Lewis dot structure is the same. You can put the dots wherever you want, really, but again, I would kind of rather you guys put them in those 4 quadrants and then start doubling them up from there. So again, I would pause the video, do lithium and neon on your own, and then push play and check to make sure you did them right. So lithium, if we look on our periodic table, it is in the 2nd period, so it has 2 valence shells. They drew those on for us. The first valence shell is going to be full, so we could add that in if we want. Again, you could write lithium in the center. And lithium is the first element in its period, which means it has 1 outermost valence electron, so we can add that in wherever we want. And then for our Lewis dot structure, we only look at the outermost. We have 1 electron, so we just put that somewhere, and we're done. Neon, find neon on our table. It's right here. It is another one in the 2nd period, which means it has 2 shells, which is right there. And then again, we can count all the way across, or we could just look at the number right here with the A, and it is 8A. So that means it's going to have 8 electrons in its outer shell. So let's do the 2 inside electrons before we forget. And then we have to do 8. So again, I would rather you guys do them in pairs so that they're easier to count. And then neon has 8 outer valence electrons and 2 on the inside. And then our Lewis dot structure, we put those 8 on here. And we're done. So one thing that we're going to look at maybe next week, I'm thinking, is compounds. So that's when these outer valence electrons will really matter, because depending on if this valence is full, which, for example, all of the elements in this row have a full valence shell, because this period can have 2 and helium has 2. This one could have 8 and neon has 8, argon has 8. So they're 8 out of 8, 8 out of 8, 2 out of 2. That means that they're not going to want to form a compound because they have all the electrons they need. And that is the whole point of forming a compound, is to either share electrons or give away or take electrons from another element. So there's 2 different types of compounds that we will discuss, and those are them. So how many electrons they have in their outer shell depends who they are going to make, or what element they are going to make a compound with. So that's kind of what we will be talking about later on. So go through the rest of this handout. It's good practice. Do the front and the back. And then for the periodic table basics, actual short answer questions, they basically are just asking questions about this sheet you did. So you only have to look at the elements that you did. You don't have to look at other elements on the periodic table. So for